Okay. Some loose ends. Doug's father is has a medical problem, so he's of course. Doug was going to prove Denny's criteria for uniform convergence. That's one of the main theorems that Doug lists there. Those theorems are ones that have been useful to us in deriving the properties of the integral, and also in dealing with some of the counterexamples like the continuous nowhere differentiable function. We needed a couple of those theorems. So I wanted to show you Denny's theorem, which is, I think anything we prove is good. Denny's criteria is usually called it. And if these things happen, I have a sequence Fn of functions defined on a compact set. Let's just call it AB. It could be another closed and bounded set, which would be a compact biannual. Let's just say AB. And here's a notation I'm going to start using. This is Fn. I'm going to say that the Fn's are monotone increasing, and they converge pointwise to the function f. An alternative would be for them to be monotone decreasing while converging to the function f. So this notation here means this is Fn of x is less than f sub n plus 1 of x, and so forth. Write these pointwise trundle up at different rates for different x's, right? For different x's in AB, the progress might be different, but the point is that they never go back. Pointwise. Pointwise monotone convergence, upward, downward. Okay, so either one of those things can happen. And Fn and f are continuous functions on AB. Nothing being claimed about the continuity or derivatives or anything. So usually we say that's C0. So if all that is true, then the convergence on AB is uniform. And why is uniform convergence important? How does that affect integration? You'll notice where it's in for integration theory. Whenever you have a limit theorem, right, commuting, taking limits, and taking integrals, somewhere along the line, uniform convergence comes into it. So, okay, how might we prove this? I was thinking about this coming over, driving down Benny Hill Parkway there. I think to do something about this. This proves I have a lot invested in it. Okay. So first of all, we have pointwise convergence. Define On to be the set of x in AB, such that let's assume the upward case here, just for definiteness. Okay, sure.
The next line from what you just passed, and then C, and you got raised to 0 there. What does that mean?
CR of S means if a function belongs to that class, it's continuous, and the rth derivatives are continuous. So the first rth derivatives are continuous on the set S. A function belongs to a class of functions that are r times differentiable with continuous derivatives on the set S. Zero just means Right, there's no claim. No claim. C1 would mean the function is continuous because it's C1, and that means the first derivative is continuous. If a function is differentiable, it's continuous. We prove that. We know that. If a differentiable point is continuous, it doesn't have to have. The technical word is smooth. You say this function is R smooth, which means its first R derivatives are continuous. So C0 just means, well, it might not even be differentiable, but the zeroth derivative, which is the function itself, is continuous. Right? Okay. And the double arrow means uniform continuous. So I had this set ON. That is, let's fix epsilon. That's always a good idea. Let's fix epsilon. I'm going to try and set ON to be the set of x's in this interval AB, where, since we're going up, f is big. So f minus fn, that's positive, of x is greater greater than epsilon. Yeah. Oh, sure hope this works. If I can figure this out, this will be an exercise. Okay. So, the picture is this. We have the limit function up here. This is f. And then here's a particular fn, say. And if epsilon is this amount, then we're looking for x's
All we're looking for n is sufficiently large for the difference between the functions. Wasn't that?
well, I have that. That's over.
Yeah.
As fn gets closer to f, this gets smaller. I think I want to turn this around.
Great. Okay.
Okay, now we have to answer a question. We'll answer that. So I have epsilon. So if this is a particular epsilon, maybe everybody in there, this would be ON, right? Because outside here, the difference between F and Fn is bigger than that particular epsilon. Epsilon is fixed in advance. All right. Now, since the Fn's are monotone increasing, what's the relationship between ON and ON plus 1? Well, if they're increasing, the difference is decreasing, right? So everything that's in ON is in ON plus 1, and then there could be some more see, Fn plus 1 is certainly no further away than Fn, and in some places might be closer. So you can only pick up points as n goes up, right? The Fn's get closer to f. So I think we can say this, right? Yep. So we note that. Okay. Now, wait. The union, n equals 1 to infinity O n, covers AB. Why is that? I'm sorry, did you see my wonderful picture, correct?